All right, boys, hope everyone's doing all right. In this video, I want to introduce you to a notion or a type of calculus problem that's called related rates problem. Okay, but before we do, I want you to recall this notion that we used during implicit differentiation. Okay, and in fact, let's rewind even farther. So if I said, what is the derivative with respect to x? That's what that means. Of, let's just suppose x squared. You would say, okay, that's a pretty easy problem. We have a nice easy power rule. The 2 comes down, the x stays in front, and then I bump the power down one. Easy schmeezy, lemon peasy, right? So this is the derivative 2x of the x squared. Okay, now, what that means is the 2x describes the instantaneous rate of change at any value x of x squared. What if, however, we looked at problems similar or pieces of implicit differentiation? What if we derived y squared with respect to x? And as we discuss, we say, okay, well, look, the y, therefore, has to be treated like an inner function because I'm differentiating not with respect to y, with respect to a different variable, x. And what I therefore, get, is by the power rule 2y, but now by the chain rule times y prime. Now we're being a little lazy when we call it y prime. What it really means is dy dx. Okay? Now dy dx, as we've been investigating, is the instantaneous rate of change of y with respect to x, right? In other words, that's the slope. That's the slope of the tangent line, the slope of the curve at a point, right? It's the instantaneous change of y with respect to smaller and smaller and smaller and smaller and smaller changes of x. Okay? We just happen to call that slope. It's a rate of change. The change of y with respect to x. Okay? Slope, of course, is a rate of change. Okay? How quickly is the function growing or shrinking or not at all? Okay? But this is comparing how y is changing, the output of a function, with respect to x. We call that slope. What if, however, we said, well, suppose r, or even r squared, is the radius of a circle, let's say, and I want to differentiate with respect to t, time. So let t be time in seconds, right? So when I differentiate r squared with respect to t, time, and let's just suppose t, time, is in seconds, mathematically or calculatically, what I get is the same thing as the prior problem. It's really structurally the same as the one above. The r is not a t, and I'm differentiating r squared with respect to t, time. And so I therefore, just like the prior implicit differentiation problem, I don't just get 2r, I get 2r by the power rule times, now by the chain rule, r prime. Now what r prime means in this case is the instantaneous rate of change of r with respect to, in this case, time. So here I have another rate. Okay, this is a rate of change. It's the rate of change, not of y with respect to x or the slope of a curve. It's a rate of change of the radius with respect to t, time, seconds. Right? So in other words, how quickly is the radius shrinking or growing? Okay, so if we understand that this dy dx is just a slope, a rate of change, then dr dt is just a rate of change. It's just the rate of change now of r, let's say the radius, with respect to t seconds. So given that, we can look at now a related rates problem. In this basic problem, here's an intro to related rates. Okay, let's suppose a circular hot plate, when heated, that should say hot plate, increases at a rate, constant rate, let's assume, of, let's say the area is increasing at, I don't know, 0.05 square centimeters rather, per second. Okay? So I might say, look, when the radius of that hot plate, I'll put the hot plate there. One of these days I'll figure out how to write and talk at the same time. When the radius is, let's say, I don't know, 50 centimeters, at what rate is the radius increasing? Right? Assuming everything is constant. In other words, the rate at which the area is increasing is constant. It's not changing. Okay? So here we have an intro to our first related rates problem. And they're word problems, and they're usually applied in some way or another. And one of the first steps that I want you to consider is, well, what do we have here? Well, hopefully it's pretty easy to see what we can draw. Is we have a circle with a radius. And we know that the area of a circle is pi r squared. And since this is talking about a circle, and then when he did, this is assuming the area, because it's square centimeters, that's the way in which we measure area, per second. That's the rate at which the area is changing, 0.05. And we're given information about the radius. So the first thing we want to do when we're solving a related rates problem is come up with a general formula, right? So here's my general formula, A equals pi r squared, that fits this model, right? It involves the area of a circle and the radius of a circle, and that's what I'm given. Now, however, this area of a circle is thousands of years old. It's static. It's not changing. So my second step is to take that area equals pi r squared and bring it to life. And I do so by differentiating both sides with respect to t time. Just like in implicit differentiation, when we have a kind of muddled, implicitly defined relation, all we do is we differentiate both sides with respect to x, and out of that comes dy dx, or several dy dx's. Okay, similar process here. I'm going to start with a boring, static, thousands of year old geometrical formula, which fits the problem. And I bring it to life by differentiating with respect to time, t. And in this case, t would be in seconds. Okay. Now I'm going to work through the calculus, right? Now I'm going to say, okay, well, what is the left and what is the right side of that new equation end up being? So the derivative of a with respect to t time is just, yep, you got it, dA dt. Now what that represents, that's the rate at which the area is changing of the circle, and we happen to know that. That's 0.05. When I differentiate the other side of this equation with respect to t time, remember pi is a coefficient, so the 2 comes down, the r is our independent variable, and now since I'm differentiating r, excuse me, with respect to t time, I need, you got it, times by the chain rule dr dt. And this is what's called a related rates equation. Okay, and it's called that because it's relating two rates. It's relating the rate at which the radius is changing, which is dr dt, to the rate at which the area is changing. Okay, you'll also note, however, there's another variable here, and that's just r. Okay, r is just the radius at any moment. Just like a derivative will have an x in it, which we can evaluate the slope of with a curve, y, at any moment. R is kind of a similar thing, right? So r is a radius. dr dt, that's the rate of change of the radius. dA dt, that's the rate of change of the area. Okay, there's my related rates equation. Now all I have to do is plug numbers into the right place and solve the problem. Okay, what I know is the rate at which the area is changing is, dear God, is right here. Here's the rate at which the area is changing. So I'm going to plug that number right into dA dt because that is the rate of change of the area. Boom. The 2 pi, that's 2 pi. The radius at that moment, just like if I'm trying to find the slope of a curve at a moment, the radius at that moment is 50. So I'm going to plug that 50 in for r. Boom. And what's left is my dr dt, which is the variable for which I am solving. At what rate is the radius increasing? That's dr dt. Okay, and now it just becomes a little bit of an algebra problem, right? I just want to solve for dr dt. So I'm going to take that dr dt, and I'm going to divide everything by 100 pi. Beep. Okay, and because I'm feeling a little bit lazy right now, I'm going to leave my answer like this. And now what I want to add is the label, right? And so note that this is the dr, the rate of change of the radius, with respect to t time. So what's the radius measured in? Well, I'm not sure. Yes, I am sure, actually. It's centimeters, right? So the radius is measured in centimeters, and time is measured in seconds. So the rate at which the radius at this moment is changing is going to be 0.05 over 100 pi centimeters, which is the change of the unit of measure for radius, per seconds, which is a unit of measure for time. Okay, so there's your first related rate problem. The general process is I would come up with a picture or diagram. That's always helpful. Then I think what's helpful is to come up with a formula, or necessary, and this is a static formula. Okay, area is pi r squared, right? And that formula has to involve the variables that are discussed or pertain to the problem. This problem that I just did has an area of a circle and the radius of a circle. So most of the time it's fairly obvious, not always. Okay, then I want to differentiate with respect to t, time. Now this is where we become calculus magicians, right? We impose rates on what is otherwise a boring formula, and then I plug and chug, right? I plug values in. Okay? Hope you enjoy this video. Next one's coming up shortly.